Record. Yes, I see it's recording. So welcome, I'm Dr. Andy Lovelace. I've worked at UW for about 20 years. I've taught about 20,000 students. And this is a new experiment for me. Sorry that I didn't do one of these for Math 125 for exam one. I just wanted to see what my capacity was. So I thought the exam two in Math 125 there's a little more going on, integration. I like talking about integration, so I hope I can help you here today. But mostly I wanted to start sharing my materials and connecting with students in a positive way where I'm not writing the test, and just can try to help people. So this is kind of for me as well, get a little more enjoyment out of this job. Anyways, I would like to, and I've taught this course many times, I really do like integration. I know this is a challenging moment in Math 125 for most students because so many pre-calculus skills come together at once. Things you didn't know you needed to know before, suddenly you need to know well. But maybe before we get started and before I show you some other things, I'm going to ask you a few questions and have us kind of blow up the chat, and then just kind of see where we're at. And I'm just kind of learning how to do these. I've only been doing this since last spring. I started doing it for my old classes, and I was like, why don't I invite everybody? It's more fun that way. So when is your exam? I think it's all the same for everybody, but let's just see that the chat works. My phone said it didn't understand me. I better turn it. It always says that to me. Okay, Thursday, great. So you have a little bit of time, which maybe means you've just gotten your studying started. For some of you, maybe it means you've done lots of studying. You currently can see my my browser and my page, correct? That was not really a question. Eventually, I'll make the browser go away. I just didn't want to forget showing you that. So in terms of topics, maybe we can do this first. I always say that, the number one thing that's going to decide how you're going to do as you finish this course is integration. There's going to be a lot of, and I'm not your instructor, so you should talk to your instructor about coverage. But I can tell you based off of experience that most instructors are going to have a lot of integration on this exam. And the final will probably start with 2 pages of integration. And so integration is your best bet at improving your grade. So that's number one. And so we should talk about some of those pieces. Which part of integration are we most worried about? Let's blow up the chat again. I see votes for trig sub. That's pretty good. Partial fractions made it in there. Work made it in there, even though it's not an integration method, but I like that. So we have partial fractions. Just a second, I got a kid. Oh, thank you, Tommy. That was the last of my coffee. Would you sit on that table?
I put creamer in it.
Oh, thank you. Would you sit on that table? I have a helper coming in. Thank you, Tommy. So then trig sub. I know this is the topic. I was prepared for that. Identifying strategies. Thank you. Sorry, my son popped in. Does your exam include arc length? That's section 8.1. No. Uh-oh. Machos doesn't. I don't think so. I'm hearing a lot of no's. It's not a major worry. I just want to make sure I know. Wonderful. Did you get to improper integrals? 7.8. Okay, this must be the last section you did, which means you did do approximation. You did Homer-Simpson's rule and the trapezoid rule, and you did approximation, and you did work. Okay. Include shells as well. Ooh, yeah, all right. That's good to know. 6.3 shells. Okay. And I think work, if I was going to guess, work, trig sub, partial fractions, and how to identify integration. 6.2 as well. All right. I like talking volumes. I'm a little less prepared for that right now, but that's going to be fine. Okay, that's helpful. What I like to do here is show you a few things because we're not going to be able to answer all your questions. And so I like to have students be able to leave and find more resources. So 2 things I want you to look at is this 125 materials. I've taught here for so long, and every quarter I would make review materials that they grew too large. And so instead of putting these on my Canvas page, I just started collecting them here. And it's not great. It's kind of a hodgepodge. But if you need practice with a particular thing, like you're not understanding how to do 7-2 trig integrals, this will get you there. Having trouble with identifying integrals, I have like, this is 30 old integrals that are just like, how would you start this? And then I say, here's how I would start them. So I've tried a bunch of different things. I have an integration table. So this is just stuff. If you're looking for a particular thing, this is the world's worst flow chart, but it kind of summarizes how we identify these different methods. So that's all there. All right. But the new thing, and this is part of the reason I'm doing this, is I realize nobody wants to read review sheets anymore. We would much rather see videos. And so I made this right here. And this is, I just made this to try to organize my YouTube videos because I have a lot. And so in particular, I made this the last 2 days. I've been working on this. You all have been my main project the last 2 days, which is this exam 2 video series. Because I'm just hoping to make a collection of these. So if you watch this, it talks about exam 2, and then I made a video for each subtopic. So this is just a little thing I've been working on. And I really dug into work and how I think about it. So I know I'm not going to satisfy everyone's questions here. So figure out where you are. You can click on the next one. You can go to the playlist, all that stuff. All right. I'm just learning how to do it. So apologies for the technology stuff, but okay. So that's it. And when this is done, I'll post it on there as well. It's here. There's 535 weirdos that actually want to listen to me right now. Okay, let's get rid of this. Let's make this smaller. Let's minimize that. So that was the main thing I wanted to say was we're not going to be able to answer all your questions, but I do have some stuff. In the end, it really is on you to engage with a lot of old exams. And there's kind of a couple ways to study, but I would look at a lot of questions and also work some in details. Okay. Question. And if somebody unmuted or something and I miss it, let me know. Mostly I'm kind of spotting the chat. So that's my agenda. We have 100 people on here. Wonderful. I'm going to make a note to myself because I meant to like take a snapshot, but we have 105 visitors. My goal is to go back to the department and say, we should do this for every exam because it's fun and because it would give us stuff to do that would be helpful to students. So that's part of what I'm thinking about. I know Clue does these things, but I think we could do it pretty well. All right. So that's it. Let's take a little preview. So a quick overview. This is from my lecture notes when I teach the course. And you can also look at my lecture notes, my paper lecture notes. But I tell students this. It sounds like yours might not quite be the same, but I say these topics. This sounds pretty close to what you said. Somebody mentioned 6-2. And then there's our rules. Mine's very clear. I have 3 pages of integrals. I say hard integrals just so that I get people thinking, all right, I got to prepare. This is the work section. I almost always have one problem about work. I almost always have one problem on improper. But I like to specifically say a few things like these things tend to happen somewhere. So you don't want to ignore them. Like you don't want to see a problem where you have to complete the square and suddenly be like, oh, I chose not to study that. So those are kind of our things. I feel like this is the one exam in our calculus courses where you know exactly what's coming, and that doesn't make it feel any better. Okay, so let's take what I'd like to do is before I completely hand over the reins and say, what do you want to talk about? I like to start with a tour of an old exam. So let's pick one. Maybe the problem is I've already made so many videos for these. I may have gone through some of these questions before, but I'm going to do the winter 2017 exam. Yo, does anyone know if you would have to prove the integral during the test? Yeah, I'll leave that to your instructor. Secant cubed is not one we usually do on an exam because it just takes a while. You could use it. I allow students to put it on my note sheet, but yeah. Okay, so let's look at winter 2017. Let me briefly share something. We're going to go back here, click here, and I should have already done this, but here is my, oops, I'm sending a private message to everyone. Here's my exam page. Just a second. That's actually my review. Here is this. And what else could we possibly want to do here? Maybe this one. I'll send this in here. Boom. All right, that's probably enough to get us going. So you might want to click on the exam archive as we are about to do a tour. And I can stay on a little longer. I am doing a Math 124 review at 8:30. So I can't stay past then. I have to prep for it a little bit too. So anyways, winter 2017, here we go. What I'd like you to do is pretend that you're taking the test. Pretend the test is tomorrow. You just walked into the test and think about the first thing you're going to write. And you can do this as part of your studying. It's a nice way to optimize your time. Get a notebook out and just write winter 2017, question 1A. And what I like to ask students to do is, what would your first step be? And then you move on to the next one. So this is a trig integral. So the thought process in general, watch my video on that, but the thought process is it one of our 4 special situations? And 3 of them are really easy to identify: trig, partial fraction, and trig sub. So the first thought, whoa, that's terrible pen. It's not my writing. Trig sub. So to me, you'll identify these right away. And this is a trig integral. This requires an understanding of the plan of attack in 7.2. But when you're doing this sort of studying, just see if you can do a first step. And if you don't know a first step, just put a question mark and come back to it. And then you move on to the next one. But my question is, think about what your first step would be here. And if not, you make a little note to look at my 7.2 video, because there's only 2 things that happened in 7.2: U substitution, or it was a situation where you had to do a half angle. And those were the only 2 things that ever happened. This is not a half angle. So it's a U substitution problem. So this problem is going to be one of the following 2 things: this or this. So the very first thing you're going to do in this problem will somehow involve those. But in order to do substitution, you have to plan for it. And so this is how I teach it. I teach it as your job is to make the derivative appear. And this derivative, there'd be a 5 here, but that would involve pulling out a secant squared. That tends to not work very well when this is odd. So it's got to be the other one: secant of 5x, tangent of 5x. And sorry, I'm squishing it in here with a 5. And so the very first step, if you understand that idea, is an unusual first step, which is this. You could also do a substitution for the get rid of the 5x if that's bugging you. But if you understand the idea of 7.2, this is the first step, which is super weird when you see it, the first time you see it. But it's setting up a substitution. And then you go, what's left standing? Tangent squared of 5x and secant squared of 5x. And I put this little arrow here because I tell students, the moment you do this, you realize you're doing this substitution. And so this thing is going to be something like 150u, but let's not worry about that. The real question I want to ask is, what do we do over here? We want everything else to be what? A secant or a tangent? You say, you lost me a long time ago. A secant. We want everything else to be a secant. This is already a secant. And so here's how I remember this. I jokingly say my brain can only hold one trig identity, and it's this one, that sine squared plus cosine squared is 1. It doesn't matter what's inside. And then I divide everything by cosine squared. Cosine squared. This is what you do if you don't have the note sheet in front of you. I do know the identity, but this is tangent squared of 5x plus 1 equals secant squared of 5x. And I want to get rid of tangent squared, so I would write secant squared. So that's how I remember. I don't have a note sheet in front of me. And that's it. It's a very unusual plan of attack, but now I can write it as the integral of u squared minus 1, u squared 1/5 du. That's about as one of the harder ones because it was a secant tangent. Okay, I spent too long there. I don't mean to spend that long when we're doing our tour, but that's what I mean is I find sometimes students come to me and they say, I was studying for the exam last night and I spent 3 hours on the first question and I'm in tears and I don't know what's going on. That's usually not a good use of studying time. So I would try to just put a little bit into each one and figure out where your issues are to get started, and then go back and do details. That's my advice. All right, let's continue our tour, and then I will stop and allow more questions. So what's the next one? So we're thinking here, and you don't tell, I guess I should we'll just practice identification here. So we have these 4 key methods, and the methods are by parts, trig, trig sub, and partial fractions. At this point, we should have a sense of partial fractions is going to look like a polynomial over a polynomial. It's going to look like a fraction. Trig is going to be trig. Trig sub is going to have a square root and some sort of quadratic underneath it, an x squared and some other stuff possibly. These have very clear signatures that you know what they are. So if it's not one of those, you're down to 2 options, either substitution or by parts. And if you know by parts, I have there's 3 things I look for. So if it's not one of these other ones, then I look for, is it a product? Oh man, my writing. I'm sensitive about my writing because somebody posted online that Dr. Lovis is the best professor ever, but boy, he has terrible penmanship. And I'm like, oh no, products, logs, and inverse trig. So the fact that this is an inverse trig, it's integration by parts, slam dunk. So we would just immediately start doing integration by parts. Was that you? All right. So sorry, I'm looking at the chat. Can you all see the chat as long as it's not private? Feel free to post publicly. I tried to share the chat in the video last time, but I couldn't. I need to, next time I do this, I'll have to do it like on a Twitch channel or something so we can all see the chat. But okay, good. So here we go. This is inverse sine. This is dx. Oh no. The way I talk is bad too. Wait till you see how I dress. Okay. Okay, what's a derivative of inverse sine? I think that's the hardest part of this problem. If I remember back, not a derivative people encounter very often. Oh, tough means good. I don't know that slang term. But don't get me started on slang because I've been joking with my kids about it. And I would like you all to eat the exam and leave no crumbs. Okay, so x sine inverse of x minus the integral of x over this. Then you still have more work to do. But the main point I wanted to make is by parts. So let's continue with thought process and not finish that problem. You say he never finished any problems. But I feel like the students that can start problems do pretty well on exams. All right, let's keep going here. Okay, what's the next? So we're playing this game of how do we start? We'll do this a little longer and then we'll switch to particular things. Oh my gosh. So the moment I see this, I know what to do. And there's a reason I know what to do. It looks terrible, which tells me exactly what to do. So if it looks terrible, I want it to not look terrible. And there's one really good technique, and nothing else jumps out at me. That doesn't look like partial fractions. It doesn't look, there's no square root. It does sort of look like a trig integral, but there's also a fraction. It just looks like a huge mess. Does anyone know the technique whenever you see a huge mess? Oh, it almost looks like a trig identity. So that gets partial credit. I like that answer. It's substitution. Mess implies substitution. Are there exceptions? Probably. But I always argue that it's never bad to do a substitution, because then you're going to have something else to look for. Okay. Any other? So before I would do identities, I would just go, that problem scares me. So then the question becomes, what do I want to do the substitution for? And this is I think substitution is by far the hardest method in 125 because it requires you see multiple things at once. So my thoughts are, we could try u equals sine and see what happens. That probably works. We could try u equals sine squared of x. Honestly, if I'm going to choose sine squared, I probably would write sine squared plus 1. We could choose, I don't know what else past that, cosine, but I'm worried about cosine. I mean, sine seems attractive to me because whenever you do a derivative, whenever you're doing a substitution, you also have to think about the derivative. You need to think about, this is why substitution is the hardest method. It's the only method that requires you see two things at the same time, a function and its derivative. That's why I think it's by far the hard. All the other techniques you learned, you just have to see one thing. This one you have to see two. That's why I think it's the hardest. So I like, Wesley, thank you for saying trying this, because I see this. That suggests that sine might be a good choice. What's the derivative of sine? Cosine. That's going to be good. So you don't really have to spend time thinking. There might be a faster way or something, but there's no reason to spend more energy. You just pick a I think the other substitution works too. You just pick a substitution that's going to clean up house a little bit. So let's do it. This is going to become u squared plus 1. This is going to be u squared. And the whole reason I saw that cosine of x dx, that's just going to become du. All right. What does 0 become? Students don't like this, but let's do it. If you plug in 0, what do you get for you? You get 0. And then one thing, I'll have you blow up the chat because I've been talking like crazy. If you plug in pi over 2, what do you get? Thank you. All right. That is a dramatic success. It's not great because the problem's not done, but this illustrates this situation. So anytime you see an integral and none of the other methods jump out, you're just going to immediately do a u substitution. I find sometimes students think, oh, I'm going to try by parts. That's a bad first try unless something else tells you to do it. Your first try is always substitution. All right, so that's an important piece of the puzzle. And sometimes substitution doesn't solve the problem. It just gives you a new problem, but I like the new problem better. So substitution kind of is like our fundamental technique always. Then you look at that one. That one looks a little bit like partial fractions to me. Now it sort of looks familiar. And partial fractions has these, my steps are this, step 0, step 1, step 2, but that's really it. Step 0 is it reduced in partial fractions? Reduced means the power on top is smaller than the power on bottom. And the answer is no, it's not reduced. So this is one of the few situations where we need to simplify. So take a moment. How do you simplify that? So suddenly I've fallen into partial fractions. Somebody was asking about partial fractions. This is a very particular type of partial fraction problem. It's long division. Yep, I would do long division. Now, a textbook and an online video would never do long division because people who do online videos, except me, like to be clever. In an online videos, they would do +1, -1. I'm certain they would do that. And then they would separate the fraction. But that only works because of this. Then you would get 1 minus. So I'm perfectly happy with that. But if we don't see that, we just do long division. It goes in there one time, subtracts. The world of online YouTube videos, for the most part, is people trying to be clever. And I would like to make videos where I am not ever clever. All right. Does trig substitution work? Yes, it does. It's not my first choice. If I can do long division, I want to do it. But it would work. What would be your substitution? What would you replace u with? Rosina. Sorry if I said your name wrong. If you want, you would do tangent. Yep, that's going to work. I have to think about how well it works, because you're going to get tangent squared plus 1 is secant squared. The derivative is secant squared. Oh, you're going to end up having to integrate tangent squared. Some people know how to do and some don't. But if you just want to stick with the variable you have, at this point, sometimes students go, okay, what's the next step in partial fractions? It's to factor. But I don't know how to factor that, which is actually good news, because that means I'm done. We're done here. This is just u minus arctangent of u evaluated from 0 to 1. And there's our answer, 1 minus arctangent of 1 minus 0. On my exam, I put arctangent of 1 on the cover. You'd be amazed at how many people still get it wrong. But we should also know it. All right, anyways. So this is 1 minus pi over 4. That's a good example of something that looks terrible. And then when we do substitution, it lands us in a place that's more familiar. Let's continue our tour. Sorry, I'm dominating. I'm trying to watch my time here. It's 7:27. But let's move forward. Again, if we don't hit your topic in as much detail as you like, that's why I have the other stuff. Just more stuff you can review later. Okay, what about this one? This one lands right into our buckets. It's right in one of our methods. Which one is it? Yep. It's a trig sub problem. Trig sub is anything that has a square root and has a quadratic underneath it. So that jumps out at me. If there's a middle term, we complete the square so that we can use our technique. So now we get to complete the square. And it has an added little, this negative has caused students many problems over the years. And it's part of the reason that I say we are not going to move. We're going to take our time in completing the square, and we're not going to move forward unless we're 100% certain we're right. Okay, I'll tell you what I mean by that. So here's my quick spiel about completing the square. A perfect square, if you, I don't know, somebody give me a whole number between 2 and 6. 3. All right, you win. If we square this, what do we get? We get x. This is just how I remember this. And it's also a chance for me to tell my few bad jokes. I'm teaching business math this term and no one laughs at my jokes ever. I told them this is a monkey face, not a single smirk. There's a nose and mouth and eyebrows. Okay. Anyways, we need to expand that whole thing out. Thanks for the gratuitous laugh. X squared plus 6x plus 9. Oh, it's painful. It's crickets. My wife says I should get a little button that makes crickets sound. Okay, here we go. So the question in completing the square is what number goes there? And you typically know this number. Okay, here we go. Half the middle is what was there because it was double to go there. So it's 3 square. And if you ever forget complete the square, you can always run that little scenario. Now, when there's a -1, it actually doesn't change the process, and I'll show you in a second. If there's a number other than -1 or 1, then I factor it out, And then I do completing the square on what's there. All right, so here we go. 27. Oh, we happen to pick the same number. Maybe whoever said that was thinking ahead. I didn't look. Half the middle is 3, squared is 9. And so it's a funny thing to do, but I'm going to write 9 minus 9. And my thought is, now I know the correct number is there. So I'm going to take a breath and be like, okay, I've done it. And now the rest is just making sure when I factor it and rewrite it that it's the same as what I started with. So this is the moment when you kind of pause. I personally don't like that negative. And so what I do is I recollect this. Oh, I keep grabbing that color. I recollect this, and this is 36. And I like to write minus. For me, I just like to take a moment and rearrange all this and write it with x squared first. Now it's going to be negative 6x plus 9. But since I did quite a few little maneuvers there, I am going to check my work in a second because I'm prone to mistakes. Okay, now it should be a perfect square. X minus 3 squared. And I don't trust myself at all, so I'm going to immediately re-expand it. X squared. When I was a student, I tried to be the first person done on every exam. And then as an adult, I realized, well, that was kind of dumb. Why didn't I check my work? I'd rather be right now. So this is 27 minus x squared plus 6x. Is that the same as what I started with? Yes. And to me, it's worth that extra moment of checking. If it's not correct, then you can go back and fix your signs. All right, so I'm ready to move forward. It's 36. So the main thing is just realizing there needed to be a 9 there. And the rest was trying to handle the signs appropriately. I'm sure there's probably better. Maybe I need to rethink how I teach that, but this gets us there. Questions that, are we okay? Half the middle squared is the method. That gets the right number in there. We're just changing the look of it. Okay. Then you kind of take a breath and say, now the problem is ready to start. This is just unfortunately something you need because we have all these methods that are good for quadratics, but they require no middle term. Okay, so now we're finally there. We have a problem that looks like this. And there is a good technique for things that look like that. It's a very clever technique involving some trig identities. I'm going to make some of our stuff disappear. So you might think about what I'm going to do next. It is trig sub, or as Lucy said, trug sub. Do you add 9 because that's the difference? Yeah, so because it's always going to be whatever this, if you just want a quick glance, you just look at this number, half the middle, squared. 9's the number I want. So that's the main thing you need. And then you add and subtract 9 in there. And then you should have a perfect square. Yep. Half the middle squared. Lovely. I like trug sub. Whoever had that typo, I think I kind of like, I want to say it that way. It's sine. It is sine. So if you don't know where this comes from, it comes from the same identity. Cosine squared plus sine squared is 1. Usually we write it this way. The reason we like to use sine instead of cosine is simply because we like the derivative better because it doesn't have a negative. But this is the identity that looks like this. Now, if you look at the tangent squared identity, it's tangent squared of theta plus 1 is secant squared. This is the identity that looks like this. And this was the clever idea someone had long ago. I don't know who's the originator of this particular method. I'm sure it's been around. Anyways, I don't know. There's a reason. There's a very particular reason we want to know this. But those are our 3 situations. And that's how you remember what they are. We want a sine here. We want a tangent here. We want a secant here. You make the identity appear. So in my head, I'm thinking, I want a sine here. And everything else is the consequences we have to face based off of that choice. Okay. So a few other things. In order to get a 36, what has to be in front of sine? A 6. We are going to do a substitution that makes it look worse in order to get rid of the radical. That's the idea. That's the whole idea of this. The reason this is important, which I think the book we should emphasize more, is because this is how you integrate when you're working under a circle. A circle is a pretty important shape, but really this is a technique for circles, in my opinion. So if you want to watch, I have videos about pancake cutting, how I cut up my pancakes for my kids, Eggo pancakes. In order to solve that question, I have to be able to do trig substitution. So there you go. There's your application. So I'm going to have x minus 3. So watch my video on pancake cutting for the motivation. So that's the substitution I'm going to make. And then I'm going to face the consequences of that. I have to remember to take the derivative. I have to remember that the whole point of this is that the square root is going to simplify to this. So I typically do all of that in the margins because I know that's what the entire goal is. The derivative left is just dx. The derivative right is 6 cosine of theta d theta. So this is 6 cosine of theta d theta. Done. And then if you know what you're doing, you know that this is going to dramatically simplify. Let's make it go. We can factor out the 36, which is the whole reason we put a 6 in there, and then we get that identity. This is what we had to anticipate. Everything we did was anticipating this moment. And so that we could write the square root of 36 cosine squared. And then it's actually 6 times the absolute value of cosine, but on the principal domain, it's cosine. I tend to talk about some of those details a little less because there's enough to worry about. So that whole thing goes here. 6 cosine of theta times 6 cosine of theta. And that's when you like take a moment, wipe your brow, and you've completed trig substitution. This is a big problem. This is probably the longest integral on this exam. This is what I do. Thank you for that question, Column. Sorry if I'm reading your name wrong. I know that some instructors draw the triangle, or some TAs draw the triangle from the beginning. I think it's kind of equal. This is just, I'm kind of stuck on my routines. So I'm not going to claim this is the best. You could back here draw a triangle. You're going to do this eventually. So whether you do it at the beginning or end is fine. This gives us a relationship. So let's talk about the triangle trick just briefly. So this is a visual way. It's funny, my daughter was just doing this in her class, but it's very unmotivated when you're doing this in, 10th, 11th grade. And it was just an offhand comment. And she did not want to hear my explanation. Okay. Okay, so here we go. We label the opposite this. We label the hypotenuse this. So that's the substitution we're using. But I do know that some people use that to help identify. What's the third side? If I call it A, get a squared plus b squared is c squared. A squared plus b squared is c squared. Yeah, so you get, oh, you're a fast typist, Allison. You win the typing chat prize. I wonder if you can, we need a way that you could share your writing. Anyways, I'll think about that. This thing actually is the same as this. And so sometimes you can be clever here and say, oh, I could just write it in the simplified form from the beginning. I don't ever require students to do that. But if you just want to have fewer parentheses, you could say, well, that's this. And that's the whole reason this all works, is because there's big connections between trig and things with radicals because of the Pythagorean theorem. Okay, that's something that's the third step. I think of this as step 1. I think of this as step 3. But you can do step 3 as part of step 1. And sometimes you can use this to think about what the values are, to realize it. So there's kind of, it's all kind of equal. But the next thing that always happens is then you are stuck with a trig integral. And that part can be long or short. It just depends on how bad the trig integral is. Yep, this is a half angle. So the moment you see an even power of sine and cosine, that's the one particular situation that the other methods don't work very well. So you bang it over the head with a half angle identity till the answer pops out. And it always works. It just sometimes takes quite a few steps. This one doesn't take that many steps because it's only one use of the half angle identity. So it's 1/2, 1. I can tell you when I was a student, I would do this and I could never remember whether it was a plus or minus. And so I just plugged in a number and I was like, okay, what happens when I plug in 0 to cosine squared? I get 1. And then I would say, well, what do I need to put between these two things so that I also get a 1? Plus. That's how I used to remember it. When you're trying to remember identity, you can do a quick experiment like that if you can kind of remember the form. Anyways, 18, and now I'm going to integrate. This becomes theta. This becomes 1/2 sine of 2 theta plus c. There's a total of 4 identities you really need to know. Sine squared plus cosine squared is 1. The tangent and secant one, I always remember from that one, so I don't even include that, but you should also know the tangent squared and secant squared one. You should know cosine squared is 1/2 1. There's a reason I'm writing this out. I'm anticipating the next question that's about to happen. 1 minus cosine of 2 theta. There's one other half angle identity I tell my students they should know. Cosine of theta. And some people call this the double angle identity. 1/2 sine of 2 theta. Let me see, Jose. If it is indefinite, we would have to go back in terms of x. Yes. So that's this last step. So we have a little more to do. So down to this last step. This is going to be 18 theta plus 9. And unfortunately, this is exactly the situation that always happens when you integrate under a circle. This actually was a circle. It was just shifted. So I know this situation well and have made many errors on it over the years. So I have anticipated what's going to happen. But if we want to return to the cleanest possible answer, we have to go back to the beginning here. And theta, there's nothing better than just writing the inverse. So sine of theta is x minus 3 over 6. The best we can do here is write 18 arc sine of x minus 3 over 6. And I hope this is okay. We're still slowly touring this exam, but people mentioned wanting to see trig sub, so I'm dominating the discussion. Forcing you to listen. All right. That piece is done. But what in the heck do we do here? If you want to use the triangle, you can't, because this is 2 theta and that's theta. And the more you work with trig, you'll learn that changing the inside here dramatically changes your function. And so it's hard to work with something that has a different wavelength in terms of doing calculus. So I'm really bothered by the fact that that's 2 theta and this was theta. I wish I had a way to get rid of sine of 2 theta so that it had a theta. That's what this extra identity is for. We move the 2 to the other side and we write this as, so this is just a special thing we need. This is the main place where we need that third half angle identity. So anyways, this becomes 18 cosine of theta, sine of theta plus c. And now we can use our triangle. I know this is a big problem. Sine is x minus 3 over 6. Cosine is that mess over 6, square root of 27 plus 6x minus x squared over 6. So it ends up being 1/2, 18 arc sine x minus 3. And this is the sort of answer you get when you're trying to cut up pancakes. You get 3 over 6. You get 1/2 x minus 3 times the square root mess. Plus c. Oh, dogs. There we go. But I like to separate the pieces. Hopefully you've got this first part done. Tough question, though. Whoever wrote this question is a huge jerk. Oh, this is one of my exams. All right, let's move forward. So we've seen a few things. We saw a trig. We saw by parts. We saw something like a mess. So we did substitution. We saw one that, all right, that we knew it was going to be trig sub, a big trig sub problem. Let's keep going. I do want to have time for work error at the end, but these are a little tamer than that one. Again, this will be recorded if you want to catch it later. If you want to watch a cleaner presentation, then you could watch the pre-made videos. Okay, what's this one? This one jumps out at you. Yeah, partial fractions. Okay, so oh, my beloved. Okay. I do. As a student, I like partial fractions. I realized there's a whole kind of collection of things in the background. So there's a lot of natural questions students ask. But really, it's a race to find A, B, and C. I might move forward. I mean, we could go to find A, B, and C. I guess we should. How do I get, let's see, thumbs up to move forward, thumbs down to find A, B, and C. Can you do a thumbs down? Maybe there's, I don't know what other, I forgot what the other emoji things were. Ooh, heart. A few thumbs down. Okay, here's what we're going to do then in a little abbreviation here. I would like you to clear the denominators. Watch this. Here we go. We're going to do a race. I haven't done this in a while. So if you have a pencil and paper, I want you to find A, B, and C. I'm going to say go. And when I say go, I'm going to find them as fast as I can. And you're going to race me. Okay. Ready? Let's clear the denominators. I can do it faster than this, but I'm not going to. I want to do it as fast as I can using only the techniques we have. I'm going to clear the denominator. AX, we'll see if the denominator is irreducible. Oh, somebody's asking something and somebody's answering it. Oh, that was, you were trying to distract me to slow me down. That's not fair. If X is 1, I get 1 on the left and I get 3 on the right. So A times 9. A is a 9th. If X is -2, let's see, I get -6 minus 2, which is -8. That's 0, that's 0. I get C times -3. I get C is 8/3. And then we're left standing to try to find B. Oh, you beat me. We're left standing to try to find B. B is going to be the coefficient of X squared. And so A plus B has to be 0 because there's going to be an X squared there, an X squared there, and there's no X squared on the other side. So B is -A. It's -1/9. Good. I want you all to be better than me. It's not that hard. All right. I'm going to leave that problem. What's this one? There's a square root hiding there. Yeah, this is a trig sub. This is a little bit tamer trig sub. X equals 2 tangent of theta. And then we're off to the races. Dx is 2 secant squared of theta. D theta, the whole reason we do this is because of what happens to 4 plus x squared. There is a square root there. It's just hiding. After you do a few of these, you probably can go straight to 4 secant squared. And that's become 2 secant. And we have the integral of 1 over 2 secant of theta to the third 2 secant squared of theta d theta. Okay, so we have 2 over 2 to the third, 1 over secant. I did a bunch of simplifying. That's the part you should do slower. I remember that students got stuck. They're like, 1 over secant is not in my table. That's true. It's not written that way, but 1 over secant is cosine. So this one works out pretty nice. I think I'm going to stop on that one and continue our tour. So when you're studying, your tour should be faster. Like, where am I getting stuck? But I wanted to hit those trig sub partial fractions. I know I didn't stop for questions, but I hope this is good. We have an improper problem. Most important thing for an improper problem is to write it as a limit. And then you just have an integral to do. Just an integral that looks terrible. And when an integral looks terrible, what's the method again? Substitution. And to me, the only logical choice is the inside here. And that's going to work. We do have a volume. Several of you said volumes are something you may need to know. I know I'm not hitting the topic of work. Usually if I open up to questions, we would do work for the entire hour and everyone would go home crying. So I think it's good we've hit these other topics. So how about a volume? Let R be the region bounded by sine of 2x, the x-axis, and between 0 and pi over 2. Please do quark. I know what you mean. Do work, please. Okay, we'll do a work problem. I think it's on the next page. I'm the worst at mistyping, so I don't have any room to talk. Okay, so this quickly though, here we go. This is a sine graph. It's going to go up. It's going to come down. It's going to go up. Great. And we're going 0. So when I plug in 0, I get 0. So let's plot that point. When I plug in pi over 2, I get sine of pi. That one's also 0. So pi over 2, 0. And it says bounded by that in the x-axis. So that's that stuff. So this other stuff I drew didn't matter. And we're rotating about the y-axis. Okay. So interestingly, this is a chance for me to talk. There's kind of a couple skills in the background when it comes to volume that are very important. One skill is the ability to label a graph. We're going around the y-axis. Okay, so in terms of labeling a graph, every problem in this course and really in Math 126 as well, whenever you're dealing with a region, it's going to start with either labeling x and trying to find a pattern based off of x, or labeling y and trying to find a pattern based off of y. And often one way is better than the other. But in order to use that pattern, you have to be able to label. So let's talk about labeling briefly, because this is a big thing I've noticed is a stumbling block for a lot of students. And it's all, not only is it something you need to do to be successful in these courses, it's something you need in general. So if somebody gives me a function and I wanted to be able to label it in terms of x, there is one clear winner here, but I'm going to talk about that just in a second. In this case, if I want to label, I would need to label this length and that length. How do you do that? And actually, I always start with a simpler example when I do this in class. And it's actually amazing. Even this simpler example is something I've seen people get wrong. So here, a little quiz for you on your labeling, because I want to get that out of the way first. I'm going to give you the parabola y equals x squared. I'm going to give you this number 9. And I'd like you to tell me how long that is. Just a quick check, sanity check. If you're looking at the parabola y equals x squared, and I give you that length is 9, what's the other length? 3. Now, in my experience of teaching calculus over many years, very commonly I see students do this. They write y here, and they write x squared here. And that doesn't make any sense because none of you squared 3. What you did was the square root. So you have to understand when someone gives you a function and this is y, this is the square root of y. And if this is x squared. And I have found that a lot of problems in chapter 6 and the whole course have to do with a misunderstanding of that basic idea. So when I look at this problem, I knew even before I got past here in the reading that I wanted to use x. There was no question I wanted to use x. I didn't even have to see the picture because I don't want to solve that for the other way. And even worse, if I go the other way, then I have 2 different sides to deal with. This side of that function and the other. I do not want to use y. That's not saying it couldn't be done. You'd have to do 1/2 arc sine of y, and then you'd have to figure out how to do it on the other side as well by using symmetry. I think it would be pi over 4 plus arc sine of y or something. It's very hard to do this way. Okay, so the point of all of that is, notice I intentionally erased the axis of rotation because the axis of rotation doesn't matter when you're making this decision. So I tell students, here's how every problem goes in chapter 6. This includes areas and volumes. You choose a variable. So you draw the region, and then you choose a variable. And you don't even consider the axis of rotation. The region chooses the variable. So based off of what I just said, which variable do we want to use in terms of what variable? Don't tell me washers or shells. I want to know the variable. X or Y? X. That's the number one piece here. So the very next thing I do is I label this X, and I want to do it in terms of X. So all students have the ordering wrong. You actually don't get to choose the method. You get to choose the variable. The variable chooses the method. It always makes me think of Harry Potter, how the wand chooses the wizard. I don't know why, but anyways, the region said we have to use X. Then you read the rest of the question. If we're using X, and I usually tell students to also label everything else in terms of X. Notice I still haven't thought about the axis of rotation. That's the very last thing I think about. Okay, now the axis of rotation is the y-axis. And that forces me to use a certain method. So you don't get to pick the method here. You have to use whichever method that gives rise to. I tell students to remember this in one of 2 ways. Are those 2 things parallel or perpendicular? Tell me in the chat. They're parallel. If you're approximating a rectangle and your axis of intersection are parallel, that means you're using shells. That requires you first have chosen your variable and drawn this. But if it's parallel, you're using shells. The other way to remember it is just to draw it. If you take this thin little thing and rotate it around, you get a thin cylindrical shell. If it's perpendicular to the axis of rotation, like if you have something like this, perpendicular to the axis of rotation, you take it around, it's a washer. So you can see how the thought process, I'm kind of emphasizing this because I didn't teach everyone here, but the thought process is you choose the variable and then the variable chooses the method. In this case, if you're using X and you're going around the Y-axis, it's shells. All right, does that help? I don't know. The moment you know it's shells, you're doing the following. You're doing the surface area of the shell, which is 2 pi times. So if you can't remember the surface area of a shell, the next time you go to the bathroom, unroll one wrap around of the toilet paper, and it's a rectangle, and it's height times circumference, which is how far around. I have a video where I show that. How toilet paper reminds me of the surface area. So this is 2 pi times the radius times the height. And we're integrating that. The integral of 2 pi times the radius times the height. It's x already, I know that. The smallest x can be is 0. The biggest x can be is pi over 2. So that's the process. Label your variable. The variable chooses the method, and then your job is to correctly put the things in there for your pattern. So the pattern for the radius is what? What goes here? Lovely. And the height, we've already labeled it. If you follow my routine for how to label things, everything's already labeled. That's it. I have somewhere, let's see if I can pull this up. Pull this up. Calc. Can you see the browser? Is it blocking everything? Uh-oh. Okay, you can see the browser. So if you go to Calc 2, I have this one called volumes, volumes, and more volumes. And that's all it is a lot of volumes. Oh, there's the other person that thinks they're going to teach you calculus. They probably are. I don't know. That didn't mean anything by that. But they're going to make money off of it. And I'm not. I have a bunch of examples here. So if you're having trouble labeling, you can check that out. Here we go. Good. Now we got a work question. We've made it. So in my mind, work problems come. Can I leave that? I didn't actually compute it. What's the technique you'd use to integrate that? Integration by parts. Thank you, Hannah. How about now? Hello, hello, hello. Nope. Speaker. Oh, I realized. Hold on if you can hear me at all. You can hear me? Did you lose me? You can hear me now. Great. Okay, I'm on the, oh, this is the microphone of my webcam. I bought a webcam last week. That was a little better. It has a microphone. It probably sounds a little different. You can hear me though? All right. I don't know what's going on. My really expensive mic has decided to not work. Yay. I can't, my end doesn't show that audio is working, but if you can hear me, great. We'll do that. I might not be able to hear you, I realize now. So somebody's been asking me questions. I might not have been able to hear you. I have a new computer as of about a week, so I'm still figuring things out, but it's way better and faster. Okay, so our goal is to find a pattern here when one or both of these things is changing. And you'll notice behind me, I have all those books stacked up there. It's because I just made a video where I talked about stacks of books, and I made a visual of it that I've always wanted to make. Just a second, I dropped my pen. I'm back. Okay, so let's see. Why can't I see this? There we go. Great. So is this a leaky bucket or a stack of books problem? And those are my own inventions, those categories. I'm sure other people use similar names, but Stack of books. I call this a stack of books problem. Really, there's two sorts of questions. There's questions where there's just one object that as it goes higher, it gets lighter or heavier. That's one type of problem. Basically, in a leaky bucket problem, the object starts at the bottom and goes up. In a stack of book problems, it's a whole bunch of items. Basically, if I take this thing, I think it says it starts full of water. So there's this. This just looks complicated. Full of water, full of water. If I stand anywhere along here, like right here, at the very beginning, is there water there? Yes, there is. There's water at that height. What about if I went 1 foot higher? Is there water there? Yes, there's water there. What about if I'm at the ear? So at the beginning of the problem, there is something at every single level. That is different than a leaky bucket problem where it's just something that started at the bottom. Okay, so the whole idea in these questions is we're going to find the effort required to lift that one example to the top. And then we're going to do it again and again and again and again. That's the stack of books. So there's one book. I don't know how you lift water with your hands, but a pump can do it. Here's another book. This book is much skinnier and doesn't weigh as much, but it gets lifted further. There's another one at the top. And I just made today the first ever video of me actually lifting a stack of books to prove that. You lift water slowly. So I would like to find the pattern. Okay, here's what we're going to do. We're going to label. If you want a system that you can label it however you want. But if you want a system that always works and is probably as general as it needs to be, oh no, I got rid of my orange. I'll just label the bottom 0. Okay, so step 1, realize it's a stack of books. Label the bottom 0 and label everything else correspondingly. This would be 3, this would be 5. Draw an example of a book here. Label its thickness. And then really what we're saying is, I would like to find a pattern. So here, if I want to be wordy, for any y, and y has to be between 0 and 3 because there is no water from 3 to 5 at the beginning, we want to find the work necessary to lift this thing. And I would like to find the pattern that works for any y. That's how every pumping problem goes. And then you just get to focus on one subdivision, one horizontal slice. Things I know already. I already know the bounds are going to be 0 to 3. Sometimes people get confused about the 5, but this is going to be where the y values are, where they start. I'm already going to have a dy here, and I already know the distance I'm going to lift. If you give me a y value, like if I give you y equals 0, the distance you're going to lift is 5. If I give you y equals 1, the distance you're going to lift is 4. If I give you y equals 2, the distance you're going to lift is 3. What is that pattern? And how am I getting that? Well, we're pumping from here to here. And it always ends up being, this is 5, this is y, what is this? And sometimes students go, well, do you always add or do you always subtract? I just think about what they're giving me. It's 5 minus y. If you label the bottom 0, this is always going to be where you're pumping to, and this is always going to be where your water starts. But you do need to understand the idea. You don't want to blindly be following. So that's the distance a book gets lifted. And now I want to find out how much this weighs. What is the weight, the pattern for the weight of this thing? And it tells me it's water. Water weighs 9,800 newtons per cubic meter. The reason you have to multiply 9.8 is because it's in kilograms. That's another discussion. So the next thing I'm going to write is 9,800. When I was a student, it helped me to think about units. This is meters. This is newtons per meter. This is meters. And your final answer should be what if you're doing work? What should the units be? Yeah, thank you for that nice message. I do think my work stuff is good. I think the videos I made today are darn good. You get to decide. It's going to be joules. Joules is Newton meters. I was really pleased to make the video of me lifting the books. So I do encourage you, if you're struggling with work, to watch that. It's 3 videos. One is the videos of me actually doing it. I made a cup and I leaked water as I lifted it, and I lifted those books. And then I did examples of each. So that'll give you more than this. There's no way I can cover it all here. But let's see what we're left with. So we're not, oh, if that's all we were thinking, we would think we're there. Oh, this is not newtons per meter, it's newtons per cubic meter. Where do I find those videos? Lovely. Let's do that now. We go here. I added them to this today. The work concept, leaky buckets, stack of books. This is the one I'm proud of. Why should I be proud of this? There's the, look at this. I'm trying to have some more fun with these classes. I'm desperately trying to get other departments to tell us the grades don't matter so much, but that's a bigger fight. But here we go. You can watch me lift this. Fun stuff. Yeah, this is this video. I am teaching Math 126 next quarter, section C and D. So that's another reason I'm doing this, is it's so much more fun to teach a course when students kind of know me already, and that's what I'm hoping for. But then I do several examples. But even in the past, this is kind of new. I'm going to make a lot of good videos next quarter. I've taught 126 a lot, so it's going to be a fun quarter. I'm also teaching 126 this summer in a hybrid format. Our department needs more students to take it in the summer because it's a bottleneck. So they're trying to see if I teach it, if I can get its enrollment up. So if it's really a big enrollment, it's good, but also bad. I don't know. Okay, so what are we left with? I'm missing something here. I'm missing actually square meters. I need the area of a slice. And so in order to finish this problem, I need length times width for this thing. Length times width. And one of those things I already know. What's the length? 4. Lovely. And now we come to the hard question. The hardest question here is, what is the pattern for the width? And a textbook would do the following. They would say, this is W, this is 2, and would use similar triangles. I'm certain this would be the textbook method. This would be a 3. This would be a Y. And that's great. So you could use similar triangles and say W over 2 is the same as Y over 3. You can order it however you want, as long as you do corresponding sides. And that means W is, I only have one complaint about that, but it's a good complaint. What do you do if it's not a triangle? Then you can't do similar triangles. And so there's another method to do this problem, which is to find the equation of the line and then use that to label it. So anyways, let's step back. There's a lot of stuff that happened right there. And let's write down a few things. Times 4 times 2/3 y dy. This was the area of the cross section. This was the density. This was the distance lifted. But really, I would have you, yeah, you could set up the equation. I'd have you watch my videos for more detail. So I did not leave time for you to ask questions. And I'm up against, let me double check something because I'm starting to doubt myself. Oh, it is 8:30. I'm up against the clock here to do my next review. So we might have to cut it short. Thank you for joining me. I hope many of you are in my class next quarter. No matter what, you still are going to have to look at a lot of old exams. So don't assume that you You're gonna need some practice, but hopefully that gave you a little snippet. All right, thanks for being here. Go ace that exam. Check out my YouTube. I also have a lot of goofy videos that I kind of want to share with students. And I'm hoping next year I could teach a seminar where we explore those sorts of questions, but that's a different thing. Oh, I heard a 9800. There's a question in there. Is the area of the slice multiplied by 9800 equal to the force? Yes. Area times thickness times 9800 is the force. Lovely. All right. Hopefully I see some of you next quarter. Good luck. Oh, what just happened? End.